And our next speaker is Madeline Marshall. We're about 1 minute ahead of schedule, so we'll get your slides up, but then we'll just hang out for a minute. That's okay, Madeline?
Yeah, sure.
Just in case people are popping in and out for specific talks, we want to make sure we stick on time. All right, I think it's time. So our next speaker will be Madeline Marshall. We'll be talking about unveiling stellar light from the host galaxies of high-redshift quasars.
Yeah, hi. So my name's Madeline Marshall. I'm a postdoc here at NRC Herzberg in Canada. And so today I'm going to tell you about what we think JWST will see when it looks for the host galaxies of high-redshift quasars. So in the local universe, there are very tight correlations between the property of a supermassive black hole and its host galaxy. So here we have the very famous black hole mass to bulge stellar mass relation. Now, we're not entirely sure why these relations exist. And so one of the best ways to understand this is to look back in time and see whether these relations existed in the early universe. So if we look at accreting supermassive black holes or quasars in the local universe with the Hubble Space Telescope, this is what we see. So you've got a very bright point source at the center of the galaxy, which is your quasar. You can still see the very extended host galaxy emission. And so from this, you can measure the stellar properties of the galaxy, like its stellar and bulge mass. So things get much trickier, though, when you go to higher redshifts. So here again, we've got images with HST. So this is WIPC3. And so this is a redshift 2 quasar. So on the left, this is what you get when you observe the quasar. And so you can see there's a very weird looking shape. And so this X shape is the point spread function, or PSF, of the telescope. And this is just what how the instrument registers one point source on the sky. And so this weird shape is the quasar itself, but there is some underlying host galaxy emission, which is being obscured by that quasar light. Now, if you do very detailed modeling of that PSF, you can subtract off that quasar light and see what's left underneath. And so in this case, you can see this very extended host galaxy emission. And so unfortunately, though, so this works well at intermediate redshifts, but as you go to the highest redshifts where we know quasars to exist, about redshift 6 and 7, we do. So this is the same instrument, exact same analysis technique. You do the PSF-subtraction, and unfortunately, we're left with no statistically significant detection. Now, this is because as you go to higher redshifts, galaxies are much smaller, and so they're not resolvable now compared to that the very bright quasar PSF. Now, it's not that there are no host galaxies there. We can actually look at different wavelengths, so particularly the rest frame far infrared with ALMA. And so we know these host galaxies are there. It's just a case of not being able to detect them because of this extremely bright quasar that's in the way. So at the moment, we cannot detect the host galaxies of high redshift quasars in the rest frame UV, which traces the stars. And so we haven't been able to measure their stellar masses or the high redshift black hole to stellar mass ratios. But that hopefully is about to change with the launch of James Webb. So this will cover the rest frame UV and optical emission of these galaxies. And so by having now the optical coverage, we hopefully will be able to see some of the emission lines from the host galaxies. But also we should hopefully be able to detect these in photometry as well, because with the massive collecting area of James Webb compared to Hubble, we'll have a much better resolution, and we hope that we'll now start to actually be able to resolve these host galaxies from that very peaked quasar emission. So questions that we've been having very recently are, will JWST be able to observe the host galaxies? And what will the best photometric observing strategy be? So to answer these questions, I've been using the BlueTide simulation to test that observational PSF-subtraction technique on mock JWST images. So BlueTides is a hydrodynamical cosmological simulation designed to study rare objects in the early universe. And so here is a zoom in on a couple of galaxies that have been formed in the simulation. Now, because it's an extremely large volume simulation, which is what is needed to have these very rare quasars. It's only been run down to Redshift 7, but we can study the Redshift 7 population. And so there are 22 SDSS-like or bright quasars in the simulation at Redshift 7. And so they are the objects that I'll be talking about for the rest of this talk. So with these quasars, we make mock images of them with the SynthObs software. And so we make mock images in both HST and JWST. And so we take these mock images and then we pass them into the observational PSF modeling pipeline that we use for our HST images. And so this pipeline has no knowledge of the real underlying galaxy distribution is. All it knows is that these are images from the telescope. So here is one of kind of the main results. So here we have a quasar that's imaged in our mock HST at the top and JWST at the bottom. And so these are in the same wavelength, so about 1.6 microns, exactly the same exposure time of 4.8 kiloseconds, which is about 2 orbits with HST. So the left image is what you get when you look with your mock telescope. So you've got that very extremely bright quasar. So after passing this through the PSF subtraction technique, we get these images here. And so with this, we can do statistical analysis to see whether that host galaxy was successfully detected. And so in this case, there was no successful detection in HST, but there was for JWST. Now, because this is a simulation, we can actually make an image of what the galaxy would look like if there was no host galaxy. And so you can see the image here. And so what we see is with the JWST image, we're seeing this yellow emission on the left-hand side from the host galaxy, but we are corrupted by a little bit of leftover flux from the quasar in the center. So doing this for all 22 of our SDSS bright quasars, we see that HST can detect none of them, while JWST can detect 10 of them. So we're seeing that JWST should be able to actually see these host galaxies for the first time, which is very exciting. But we're not stuck with that observational strategy that was used with HST. We can look at different exposure times. So this is one quasar with different exposure times in the top panels. And then we can look at the different filters. So we've focused on the near-cam broadband filters here. We've also looked at a couple of the MIRI filters as well, which I'll mention in the next slide. So here we plot the fraction of successful detections as a function of wavelength, and I'll slowly step you through this. So first of all, if we consider the purple points here, these are the near-cam wideband filters in 10 kilosecond exposures. And so you can see that particularly for the long wavelength near-cam filters, this performs extremely well. So we're detecting more than 85% of the host galaxies of bright quasars, which is just very exciting. The short wavelength filters perform slightly worse, but still a lot better than the HST images, which detect none. So if we now consider the same filter but different exposure times, so we've got 1, 2.55 and 10 kilosecond exposures, we see that we really need about 5 kilosecond exposures or more to detect the majority of host galaxies. Now finally, we also consider MIRI, and so we find that unfortunately even 10 kilosecond exposures with MIRI will result in less than 30% successful host detections. So we have made all of these detailed predictions about what we think JWST will see and what the best observing strategy is. And so that guided our JWST Cycle 1 proposal, which we were very lucky to be successful. So we have 16 hours to observe 2 Redshift 6 quasars with the aim of detecting their host galaxies. So we hope to characterize the rest frame UV and optical properties of these hosts for the first time, measure the black hole stellar mass ratio for high-redshift quasars in the early universe, compare the stellar properties from JWST to the gas properties that have been measured with ALMA, and also study their environments. So this is going to be very exciting, and we're hoping that it will actually show us these host galaxies for the first time. But we're not the only people that are going to be looking at high-redshift quasars with JWST. So I've made a compilation of all of the geo programs that will be targeting high-redshift quasars. And so we've got each of the different instrument modes highlighted in different colors here. So you can see kind of trying everything. Near-spec IFU, though, seems to be a very popular strategy for trying to understand these really exciting and extreme systems. So that's the geo, and then there's also a lot of guaranteed time observations which will observe these objects. And so overall, this is going to be a very exciting time for high-redshift quasar science. So to summarize, I've been using mock images from the BlueTide simulation to test PSF-subtraction on JWST images to see if JWST can detect quasar host galaxies. The answer, in short, is yes. So we find that more than 5 kilosecond exposures with a near-cam long wavelength filters should be the most successful strategy and should detect the majority of quasar hosts. So these predictions guided our JWST Cycle 1 observations, which hopefully will detect 2 of these quasar host galaxies. But overall, there's going to be, I've counted 418 hours in JWST Cycle 1 dedicated to high-redshift quasar science. So this is an extremely exciting time to be involved in this area, and hopefully if there's a SAZERAC conference next year, we might start to see some of the first results. So stay tuned, and it's certainly a very exciting time.
All right, thank you very much. So we'll have some time for questions. We'll wait a little bit for people to type them, although we've already got a few. So maybe when you're ready, Steve, you could ask the first one.
Yeah, I was going to say we're kind of inundated with questions already. So have you looked at how accurate stellar masses and I guess other physical properties are in your simulated James Webb galaxies?
Yeah, so masses, no, we haven't gone that far, but magnitudes and radii particularly. So one thing that will be an issue and needs to be very carefully considered is any residual quasar flux. So if you take account for that, you can actually get very accurate measurements of the magnitudes and extents of these objects. Morphologies are going to be trickier because of that central region being contaminated, and also because the signal to noise will be quite low. But yeah, it actually is, it seems like it will do a really good job. So there's a whole section in the paper about that if you're interested in taking a look.
Thank you. So the next question was about the specific quasars that are going to be observed in the observations you talked about. Do you know, can you comment about what's known about the large-scale structure around those 2 quasars?
So we've picked these, so we observed these with HST and have done the detailed PSF subtraction for those. And we found that one of them actually has very nearby potential companion galaxies, which is part of the reason we're interested in looking at this one. Whereas the other one, certainly in its local environment, seems to be more isolated. So it seems like it's not potentially an ongoing merger. I don't know about their larger scale environments, but certainly we've picked kind of one from each of the local environments.
Great, we have some more questions. So what do you think are the prospects of deconvolving the AGN and the host with the rest frame optical spectroscopic data, for example, using the IFU or the GRISM? Would you expect the contrast to be smaller or larger compared to the continuum, i.e. the broadband imaging?
Yeah, it's a good question. I think with the GRISM, I think things will be easier because you've got the very strong line detections. I think the prism, it will be tough. I'm thinking potentially one way of going about this is to basically make broadband images from the prism and do the same kind of technique that we're doing with our raw broadband images. But yeah, things get smeared out a lot more with the lower resolution spectra. So I think that might be tougher, but we're still hopeful. I mean, there are certainly a lot of teams targeting this, and basically we're trying every strategy that there is. So I think if it's possible, one of us will see these. So yeah.
Great. We've got time for one more question to head here. So about the simulations, do you apply any spreading to the particles before applying the PSF? If so, how do you approach that for each particle type?
Yeah, so these images are from just the stellar particles. And so that is, the images are smoothed, and then it's also then convolved with the PSF of the instrument. And then there's noise added, both shot noise and sky noise. Yeah, I can give you more details in the Slack.
Okay, great. Thank you. Yeah, and there are a number of other questions in the Slack. So
Sure.
if you want to head there after this session. Thank you very much. Yeah, thank you very much, Madeline.